Okay, so hello everybody. Today, welcome to the Mu problem party session. Today we're gonna be talking about derivatives, and this lesson is mostly gonna be going through like the mechanics of derivatives, how to like compute them. And I think next month we'll probably work on like the applications of derivatives. So like what can you do with them? How can you apply them? Um, so let's just jump right into it. So last time we talked about limits, and so we're going to actually start getting into like the meat of like what calculus is. So one of the reasons calculus was developed is that mathematicians wanted to know if you could calculate the slope of a tangent line at a certain point on a graph. So if you have some curve like that, and this is like, pretend that's tangent, I know that's kind of badly drawn, but we want to see if we can find a point on the graph, the tangent line to that one point on the graph. And so this was like a big problem for a long time. And the way that they were able to solve it is by using the limit concept that we learned last time. And so what they did is they first took 2 points on the graph. Let's say this is a comma f of a, and this is b comma f of b. And they drew a line through that like those 2 points. Let me actually draw this better. Sorry, it'll make more sense if it's like this. So we call this a secant line. It's not tangent yet, but we can also, I'm gonna also call this actually a plus b, sorry, comma f of a plus b. And so this is called a secant line. And so we can calculate the slope of the secant line by doing f of a plus b minus f of a over a plus b minus a. And so this is equal to f of a plus b minus f of a over a. And so this gives us the slope of the secant line, but we want the tangent line. And so what we can do is we can take this point and bring it closer and closer to this point. And so what that'll do is as it gets closer and closer to the other point, it'll approach the tangent line. And so if you remember from last time when you were talking about limits, one thing that was pretty like important about it is that even if some like function doesn't exist at that point, what we can do is we can approach that point and then it'll give you like a value that you can work with. And so here, what we're trying to do, oh, sorry, this is b. So we have b and we're trying to make b as small as possible because that'll approach a. And so what you'll have is like 2 points that are like infinitesimally close to each other, and that'll give us the tangent line at that point. And so the way that we write this is the limit as b approaches 0 of f of a plus b minus f of a all over b. And so yeah, that's pretty much how we define a derivative. So let's look at some like actual examples of how we can do, like how we can use this. So let's start with f of x is equal to x squared. We want to find the derivative of f of x equals to x squared. And so remember, that's equivalent to saying, what is the tangent line at every point on the graph? And so if we use our formula that we got here, we can write this as the limit as b approaches 0 of x plus b squared minus x squared all over b. And so if you don't know where I got that, I just replaced a with x here and I just kept b the same. And so when we expand this, what happens is we get x squared plus 2xb plus b squared minus x squared all over b. And this is equal to the limit as b approaches 0 of 2xb plus b squared over b, which is the limit as b approaches 0 of 2x plus b. And so now we can just like, it's not an indeterminate form of anything, so we can just plug in 0 and we'll get 2x. And so this 2x kind of like, it's kind of weird because what we just did was like, we're kind of used to before from like plugging in numbers into a function and getting a number out. But a derivative is what we call an operator, and it acts upon functions. And so when you apply the derivative operator on a function, you get another function out of it. And so the way that we write this is called Leibniz notation, I think. Is you'll see this fraction, but make sure, like, keep in mind it's not a fraction. If you use this as a fraction, you'll probably get a lot of stuff wrong. But we write this as like this d over dx of x squared is equal to 2x. And so what this is basically saying is that if I were to take the graph of x squared, which is a parabola, and then I were to plug in values of x at points along the graph. So let's say I wanted to find the tangent line at x equals like 1, for example. Then the slope at x equals 1 will have a tangent, the tangent line at x equals 1 will have a slope of 2. And so that'll look something like that. And so if we want to actually find the tangent line itself, what we can do is we know that, and we want to find the tangent line x equals 1, we know that it passes through 1, 1, because we're f of x is equal to x squared. And the derivative at x equals 1 is 2. So it has the equation of the line will have a slope of 2. And using the point slope formula, we get y is equal to 2 times x minus 1 plus 1, because it passes through 1, 1. And so the equation of the tangent line is y equals 2x minus 1. I also want to go through other ways we represent derivatives. So another way is if you have f of x is equal to x squared. One way that we write derivatives, another way that we write derivatives is f prime of x is equal to 2x. Then sometimes, and so the main two ways we represent derivatives is using the Leibniz notation. So d over dx times of x squared is equal to 2x. Or if you have like f of x is equal to x squared, then f prime of x is equal to 2x. So that's basically what, like, conceptually what a derivative is. And so if we also, really quickly, if any of you guys have like any questions at any point, I know sometimes some people said last time that I was going kind of quickly, you guys can just like message me or Sharvaa in the chat, and then we can answer your questions. And yeah, so let's keep moving. So let's talk about like different things you can still like do with derivatives. So let's say you want to take the derivative of x squared plus x x squared plus x plus 1. So before I get into more like how to solve derivatives, let's talk about like what you can do. So for example, we call derivatives are a linear operator, which means that you can split this up into like the sums of the derivatives. So this is equal to the derivative of x squared plus the derivative of x plus the derivative of 1. And so before we know how to calculate what these derivatives actually are, this is just like how we represent derivatives. And so another thing is you can pull out constants. So if you have the derivative of ax squared, that would be equal to the derivative a times the derivative of x squared. And now if you want to evaluate actual functions, the most important like rule for polynomials is it's called the power rule. So in general, the derivative of x to the n is equal to n times x to the n minus 1. And so this is true. Actually, I should write this as a real number. So if r is a real number, then the derivative of x to the r is equal to r times x to the r minus 1. And so this is true for r, all r, except for r equals 0. Because if r equals 0, then you have the derivative of some constant c. And if we were to graph that like a constant, then you can see that the slope at every single point is equal to 0. So the derivative of the constant is just equal to 0. Also, Sharvaa put a problem set in the chat, and so if you are like more advanced and you've already done like calculus and you want some like harder problems, then that's in the problem set. Also, really quickly as an aside, If you want just more practice problems on derivatives, I would like Paul's online notes is the best like resource ever. I said this at the last meeting as well, and I'm going to say it here because I love Paul's online notes. But if you want to use Paul's online notes, it'll give you really good like fundamental practice problems that will get you like how to solve like just basic derivatives if this is confusing you. Okay, so moving on, let's talk more about different like functions that we can take derivatives of. So the derivatives of the trig functions are as follows. So the derivative of sine x is equal to cosine x. The derivative of cosine x is equal to negative sine x. The derivative of for now, let's just take these two, and then let's see what we can do with them. So this is like also the derivative of e to the x is equal to e to the x. And the derivative of ln x is equal to 1 over x. So if you just Google like common derivatives, they'll like a giant table will pop up and all of these will be in there. And so these are some things that like you just need to have memorized. Like all derivatives of like all the functions that you've seen before, you'll probably be asked to take a derivative of them at some point. And so I think it's really important again to like just know where we've come from. So we started with this idea about talking, like for example, let's draw a sine of x. We want to find the tangent line at certain points. And so the slope of the tangent line at certain points on the graph, if you plug that, like if you want to find the slope at like x comma f of x, you can plug that into the derivative, x into the derivative, and that will give you the slope at the tangent line. And so I think it's like kind of cool or like beautiful or whatever you call it, that for example, like the derivative of sine of x is cosine x. And so you can plug like values into sine of x and get the like slope of the tangent line at certain values of x. So right now we can only still take like derivatives of like simple polynomials. So if we had, for example, 2x squared plus 2x plus 1. So using the rules that we have from above, we can separate this like this. So 2 times the derivative of x squared plus 2 times the derivative of x plus the derivative of 1. And so we talked about how the derivative of x squared was 2x above. That'll just be 4x. The derivative of x is going to be, so we have x to the 1, right? And so using the power rule, like we talked about, we bring the 1 down. So it's 1 times x of 1 minus 1. 1 minus 1 is just 0. So it's just going to be 0. So derivative of x is 1 because x to the 0 power is 1. And so that's plus 2. And then remember that the derivative of a constant, oh, sorry, I should have written that. The derivative of a constant is equal to 0. And so here we have that the derivative of 1 is equal to 0. So when we took the derivative of 2x squared plus 2x plus 1, it's equal to 4x plus 2. Let's do another example with sine of x. Let's do sine and cosine. So the derivative of 2 sine of x plus 3 cosine of x. This is equal to 2 times the derivative of sine of x plus 3 times the derivative of cosine of x. And so if we look back to our table, the derivative of sine of x is just cosine of x. So 2 times cosine of x plus 3 times the derivative of cosine x, which is just negative sine of x. So this is negative. So negative 3 sine of x. Let's do one more and then we'll get on to like more stuff about derivatives. Let's do the derivative of x squared plus e to the x plus 3 sine x minus 5. So this is equal to the derivative of x squared plus the derivative of e to the x plus 3 times the derivative of sine of x plus the derivative of negative 5. So from above the derivative of x squared, we bring down the 2. because it's n times x to the n minus 1, and then, or like r times x to the r minus 1. So you bring down the 2 and you subtract 1 from the exponent. So it's just 2x. Then the derivative of e to the x is just e to the x. You can find that in our derivative table here. And then the derivative of sine of x is just cosine of x. That's also in the derivative table above. And the derivative of a constant is just 0, so it'll be plus 0 here. So the derivative of like this expression was 2x plus e to the x plus 3 cosine of x. And so we know how to do just like simple, like if we just add and subtract with like constants and stuff, then we know how to take the derivative of like most of those. But for example, if I ask you to take the derivative of tangent of x, we don't know how to do that. But what we can do, we can write the derivative. Actually, sorry. Let me start from let's start with particle. So let's say we wanted to take the derivative of something like x squared times e to the x. Then you can't just, one important distinction to make is this is not true. I wish it were true. It would make my life so much easier, but it's not true. That's wrong. Please don't do this. You'll get a question wrong. We have to use something called the product rule. So if you're taking the derivative of f of x times g of x, that's going to be equal to f prime of x times g of x plus f of x times g prime of x. So this like kind of seems like it's coming out of left field, but once we talk about different other types of like methods for derivatives, then I can like talk about this a little bit more. But just know that the product, this is called a product rule. Let me actually. So the derivative of two functions multiplied is equal to the derivative of the first function just times the like the derivative of this, like not the derivative of the first function times the second function plus the first function times the derivative of the second function. So this will make a little bit more sense when we let's go back to the example we had above, the derivative of x squared times e to the x. So to do this, we have to take the derivative of x squared, multiply that by e to the x, and then add it to x squared times the derivative of e to the x. And so the derivative of x squared is just bring down the 2, and then you have 2 minus 1 at the top times e to the x plus x squared times the derivative of e to the x, which is just e to the x. So this is 2x times e to the x plus x squared times e to the x. If we had like a little bit more, I guess like a more difficult problem, let's do the derivative of sine x times e to the x. So this would just be the derivative of sine of x times e to the x plus sine of x times the derivative of e to the x. And so the derivative of sine of x is just cosine of x. And then the derivative of e to the x, sorry, we're not taking the derivative here, sorry. So the derivative of sine of x is just cosine of x, and then you multiply that by e to the x plus sine of x times the derivative of e to the x, which is just e to the x. So we can write this as e to the x sine of x plus cosine of x. So that's called the product rule. Then we also have something called the chain rule. That's basically saying that if you have some function y is equal to f of g of x, then the derivative of y. Oh, also something that like I was pretty confused about at the beginning. I've been writing derivatives as d over d of x, but if you want to take the derivative of y with respect to x, then it'll just be dy over dx. And so this basically, if I can write dy over dx as f prime of g of x times g prime of x. And so again, what this means, this is like, it's kind of like hard to understand at first, but like it'll make more sense when you do an example. But what this is basically saying is you take the derivative of the outer function, but then keep the inner function constant, and then you multiply that by the derivative of the inner function. And so, for example, let's do sine of 2 of x. And so with chain rule problems, it's always helpful to write them as, like, at least when you're first starting out, to write them as like what is f of x and what is g of x. And so what we need to do is we have to say that f of x is equal to sine of x. And we say that g of x is equal to 2x. So then that would mean that f of g of x is equal to sine of 2x. And so if we use the formula we have above, the chain rule, we can say that the derivative of this is equal to the derivative of sine, which is just cosine of 2x, times the derivative of 2x. And then the derivative of 2x is just 2, because x is like x to the first power, and so you bring that like 1 down and you subtract 1 from the exponent, so it's just 1 times x to the 0, which is just 1 times 1, which is 1, and so you multiply that by 2, so it's just 2. So this is just equal to 2 times cosine of 2x. Let's say we had the derivative of e to the x squared. So here your f of x will be e to the x, and your g of x will be x squared. So that means f of g of x is equal to e to the x squared. And so now if we do our chain rule, we'll get the derivative of f of x, which is just the derivative of f of x, which is just e to the x. But remember, it's f prime of g of x, and so we still have to keep that x squared in there, I guess. And so that's just e to the x squared times the derivative of g of x, which is derivative of g of x. And so the derivative of x squared again is just, you bring the 2 down and you subtract 1 from the exponent, so it's just 2 times x to the 2 minus 1, which is just 2x. So this is equal to, oh sorry, I wrote this kind of badly. This is equal to e to the x squared times 2 of x, which is just 2x e to the x squared. Let's do one more example of product rule. So let's say you have the derivative of sine of x to the 7th. Actually, let's do 2. Sine of e to the x plus 3 to the 7th. So when you have something like this, this is like 3 functions inside of each other. So if we were to do our f of x, g of x thing, we have that f of x is equal to sine of x. G of x is equal to x to the 7th. And h of x is equal to e to the x plus 3. So it's like kind of like confusing how we got here, but like let's do f of g of h of x now. So f of g of h of x. So that's equal to f of g of h of x, which is just e to the x plus 3. G of e to the x plus 3 is just e to the x plus 3 to the 7th. And then now if we like apply f on that, we have sine of e to the x plus 3 to the 7th. And so if you have like 3 functions inside of each other, then what we can do is that we can like the chain rule for 3 functions is like basically the same. All you have to do is treat this inner function as like just g of x. And so what that looks like is if you have the derivative of f of g of h of x, that's equal to f prime of x times g of h of x, right, times the derivative of g of h of x. And the derivative of g of h of x is just, let's rewrite this first. Is just g prime of h of x times h prime of x. And so this is equal to, let's see, so our f is sine of x. So the derivative of sine of x is just cosine of x. So we have cosine of g of h of x. So g of h of x is this e to the x plus 3 to the 7th. So we can do e to the x plus 3 to the 7th times g prime of x. Our g is x to the, g of x is x to the 7th. And so if we take the derivative of x to the 7th, you just bring the 7 down and you subtract 1 from the top. So that's 7 times x to the 6th. And so it'll be 7 times x to the 6th, but you're plugging in h of x here. So your h of x is e to the x plus 3, so it'll be e to the x plus 3 to the 6th. Then if we have h of x, we have to take the derivative of h of x, which is just, let's see, so h of x is equal to e to the x plus 3. So then the derivative of h of x is equal to the derivative of e to the x plus the derivative of 3. The derivative of e to the x is just e to the x, and the derivative of 3 is just 0. And so your h prime of x is just going to be e to the x. So the derivative of this ginormous function is this here. Does anybody have any questions? I know I went through a lot really, really quickly. But yeah. Okay. If this is super basic for you, I'm sorry. If this is really fast for you, I'm also sorry. But if you have any questions or anything, just feel free to send something in the chat. Okay, let's keep. I think actually Sharvaa can pick it up from here.
Okay, let me share my screen. You might have to. Okay, yeah. Start broadcast. Tell me if it worked. Yeah, I think it did. It did, right?
Yeah, it did.
Okay, so we're gonna start off. I think we can start off by just doing some practice problems. Just going back and just letting you try a problem. For example, let's try doing the chain rule. Say that we have say the function is f of x is equal to sine of e to the 2x, right? Try doing this derivative, and what is f prime of x? Okay, so going back to what we were talking about before, in this case, notice that the outer function f of x would be sine of x. But then the inner function is e to the 2x, right? But e to the 2x is not an elementary function, so we can split it up even further. Let's say that g of x is x squared, and h of x is equal to e to the x. And the reason we're able to do that is because notice that if you square e to the x, you end up with e to the 2x. Now, if we keep going, remember what we said before, f of g of h of x, the way you take the derivative is it's kind of like an onion ring, right? You first start off at the outer, you start off with f of x, it's the outer function, you take the derivative of that, and you get f prime of g of h of x. But then you move on to the next layer. The next layer is g, right? So then you take the derivative of g and keep what's on the inside. So then you get g prime h of x. And finally, you multiply times the derivative of the inside ring, which is h prime of x. If you do all of that, you get f prime of g of h of x. F prime of x we know is cosine of x, right? The derivative of sine is cosine. So then you get cosine of x squared, but then x squared of e to the x. So then it becomes e to the 2x times g prime of h of x. That's 2x. The derivative of x squared is 2x. And then you do 2 x, but you're plugging in e to the x, so you get 2e to the x, 2e to the 2x. And then finally, h prime of x, that's the derivative of e to the x, so you multiply times e to the x. If you expand this all out, you get your final answer. And we can simplify it a little further if you want. You can write it as 2 cosine of e to the 2x times e to the 2x plus x. Okay, so that's the derivative of sine of e to the 2x. But now we're going to start learning some other techniques. So we've talked about product rule and we've talked about quotient rule. We talked about product rule and we talked about chain rule. So now we're going to learn something called quotient rule. And so quotient rule is going to be whenever you have any kind of fraction and you want to take the derivative. So it's going to be always of the form f of x over g of x. And if you were to take the derivative, let's call this function h of x. That means that h prime of x is going to be low d high minus high d low all over low squared. So there's a little phrase you can use to remember this. So it's going to be low d high minus high d low all over low low. And so mathematically, what does this actually mean? Well, the low is going to be the lower function, the d is going to be derivative, and high is going to be the upper function. So low is g of x, d high is going to be the derivative of the upper function, so f prime of x, minus high d low, so minus f of x, the higher function, times the derivative of the lower function, which is g of x, so g prime of x, all over low low, which is g of x squared. Mathematically, you can remember as low d high minus high d low all over low low or all over low squared. So let's try an example using this formula. Say you want to find the derivative of x over sine of x. Well, to do x over sine of x, we start off, we say the upper function f of x is equal to x, and the lower function g of x is equal to sine of x. So we do low, so the low function, times the derivative of the high function, so times 1, right? The derivative of x is 1, minus high, so x, times the derivative of the lower function, which is the derivative of sine of x, which is cosine of x, all over low low, so g of x squared, which is sine of x squared. Obviously, you can simplify this a little further. You can split it up as like 1 over sine of x minus x cosine x over sine of x squared. Or you can keep it in that form. Whatever the answer choices have, you can submit. So this is quotient rule. And a lot of the time, quotient rule, it's more about being careful. You just have to make sure you keep track of everything and that you're taking the derivative of the right function at the right time and you're subtracting in the right order. Remember, it's low d high minus high d low, not high d low minus low d high. So that's the quotient rule. From there, we can talk about a new strategy known as, we can try one more example actually. Another example would be something like x minus 1 to the 5th over x squared. Now, this is another example of quotient rule, and it's pretty obvious because you have something on top and something on the bottom, and you want the derivative. If we were to take the derivative of this function, let's call it h of x again, and you want the derivative, but let's say this time they want the derivative at a certain value. Imagine they want the derivative of h of x, but at the value of 2. How would we go about solving this? We set up our same equation. We say f of x is equal to x minus 1 to the 5th, and g of x is equal to x squared. But this time, notice that the top function isn't just one of our elementary functions. You can't just take the derivative immediately. We're going to have to use our chain rule, right? Because it has two functions involved. It has the x to the 5th and the x minus 1. So we first analyze what is a f prime of x. Well, let's say f prime of x. Well, we can say that the derivative of f of x, well, we split it up, right? We say that, let's say m of x is equal to x to the 5th, and n of x is equal to x minus 1. Well, then we're trying to find the derivative of m of n of x, right? We want the derivative of x minus 1 to the 5th. Oh no. Did the screen share go out? Srijan Tanmay,
Yeah, it's gone.
it's gone. Okay.
Yeah, it is gone.
Try to fix that. In the meantime, I guess we can do something else. Quotient. In the meantime, I'm just going to share something else. You can just look at this while we're waiting. This is just a list of all the different formulas that you need to know. The power rule, the product rule, the quotient rule, and the chain rule. And so if you know all of this, the FAMAT problems should be, like the derivative problems should not be too hard. My iPad's back, so let me just get into the Zoom. Let me join the breakout room. Okay. My iPad's back, so share screen. Okay, we're back. The screen share should change now. Screen. Okay, we're back. Okay, so going back to where we were, we want the derivative of h prime of 2. And remember what we said. We can write it as m of x. Okay. Okay. So taking the derivative of x minus 1 to the 5th, remember what we said, we'll write it as two functions. We'll write it as m of n of x, where m of x is equal to x to the 5th, and n of x is equal to x minus 1. Remember what we said, the derivative of this is m prime of n of x times n prime of x using the chain rule. M prime of x is 5x to the 4th. Remember the power rule, you bring the 5 down and you get 5x to the 5 minus 1, which equals 5x to the 4th. So then m prime of n of x is 5 times x minus 1 to the 4th, right? Remember n of x is x minus 1, so 5 times x minus 1 all to the power 4 times n prime of x. The derivative of x minus 1 is going to be the derivative of x minus the derivative of 1. The derivative of x is just 1, and the derivative of a constant is 0. So you just are left with 1. So our final answer is 5 times x minus 1 to the 4th. But why did we do all of this? This was all simply to find the derivative of f of x. So we can take all of this work and we can make it really small, because our main goal out of all of this was to find the derivative of f of x. So we can say that the derivative of f of x, or f prime of x, is equal to 5 times x minus 1 to the 4th. Okay, where do we go from here? Well, we know g prime of x is equal to 2x using the power rule, and we know f of x and g of x. So now we use our quotient rule, low d high minus high d low all over low squared. So in this case, its low is x squared times the derivative of high, which is 5 times x minus 1 to the 4th, minus high d low all over low squared. In this case, low squared is x to the fourth. X squared squared is x to the fourth. So we get our final answer. Obviously, you can simplify this by taking out an x from the numerator and x in the denominator, and we can rewrite it as x cubed on the bottom and x and cancel out an x there. So you're left with 5x times x minus 1 to the fourth minus 2 times x minus 1 to the fifth all over x cubed. Okay, so that's quotient rule, but just moving on from the traditional product rule, chain rule, and quotient rule, there's one more main strategy when it comes to taking derivatives, and something known as logarithmic differentiation. And so first, let's do a quick review of logarithms. So in alpha and theta, you might have learned that the natural log of two numbers multiplied, so ln of like 2 times 3, is equal to ln of 2 plus the ln of 3. And this is just traditional exponent rules. When you multiply two things inside an exponent, you can just split it up and write it as two additions. But you can also apply this to functions. For example, if you have the natural log of x squared times sine of x, this is equivalent to the ln of x squared plus ln of sine of x. And you can actually go a step further. Using what we've learned from exponent rules, remember that also if you have a power inside of an exponent, you can take out the power and write it on the outside. In other words, you can write ln of x squared as 2 ln of x, right? Because you basically take the exponent and move it to the outside, and you get 2 ln of x. And then this is equal to still the same ln of sine of x. But how does this actually help us? Well, when it comes to derivatives, we need to know first that the derivative of ln of x is equal to 1 over x. In other words, say that we have the derivative of ln of, say we want the derivative of ln of sine of x. Well, this becomes our chain rule, right? The outer function f of x equals ln of x, and our inside function g of x is equal to sine of x. Now, if we move on, and now if we try the chain rule, remember what we said. It's f prime of g of x times g prime of x. Okay, but what's f prime of x? F prime of x is 1 over x. So that means f prime of g of x is 1 over sine of x, and g prime of x is the derivative of sine, which is cosine of x. In other words, you get cosine of x over sine of x. And in trig, you might know that this simplifies to cotangent of x. The main thing to realize is once you know the derivative of ln of x is 1 over x, it just becomes a chain rule. But that's not what logarithmic differentiation is about, though. Logarithmic differentiation is very useful when you have a product of multiple things all at once and you want to take the derivative. In other words, it would look something of the form x squared times 1 minus x to the fifth times 4, you'd have something like 2x cubed. Say you have something that looks like this. Well, what logarithmic's really good for is that it basically lets us take, say this is equal to y, right? It basically lets us take the ln of both sides. You'd get ln of y is equal to the ln of x squared times 1 minus x to the fifth times 2x all cubed. Now, if we take the derivative of both sides, there's one thing we have to be really careful about. When you take the derivative, you get 1 over y, but remember, y is actually a function of x, right? So let's say you have y, right? When you take the derivative of y, you get 1, but you have to multiply times dy dx. And so we'll get into something known as implicit differentiation in a moment, but let's just continue with this example. So you get 1 over y times y prime is equal to, or we can write as dy dx, I guess, is equal to ln of x squared, the derivative of ln of x squared. So we want the derivative of this all. So we can continue, we can first simplify down ln of y as ln of x squared plus ln of 1 minus x all to the fifth plus ln of 2x cubed. And if we simplify this further using our exponent rules, you'll get 2 ln of x plus 5 ln of 1 minus x plus 3 ln of 2x. Okay, now let's take the derivative of the right side. Well, what do we get? If we take the derivative of the right side, you get 2 over x, right? Remember, ln of x derivative is 1 over x plus 5 over 1 minus x. But remember what we said about chain rule. You have to, once you take the derivative of the outside and plug in the inner function, you have to take multiplied times the derivative of the inner function. In this case, the inner function is 1 minus x, whose derivative is -1, plus 3 over 2x. But remember, you multiply times the derivative of the inner function, which is 2. So you get 3 over 2x times 2. Simplifying this down, you get 2 over x plus, or I guess we can write it as 5 over 1 minus x plus 3 over x, which simplifies to 5 over x minus 5 over 1 minus x. But that's just ln of y. Now, that's how you simplify down these ln functions down into a nice form and then take the derivative. But that's the derivative of ln of y. Now, before we can actually finish this problem, we need to learn a concept known as implicit differentiation. So implicit differentiation is going to be used when you have something that's of the form like x times y. Now, we can't just take our traditional derivative, because remember, when we take a derivative like x squared, what happens? You do the derivative of this, you bring down the 2, and you get the derivative of this is equal to 2x. But now we're looking at something a little more complicated. Now we also have a y involved. So what do you do when you have a y involved? You have to treat it as its own function. You have to treat it and then treat it as its own function, g of x, okay? And then you have to use our other rules that we've learned, like product rule, chain rule, to then see how we can actually use it to solve these problems. Okay, so let's do that. We write x is just x, but then y, we treat it as its own function of x, the y of x, right? Now, we want the derivative of this. And this is our traditional product rule, right? We take the derivative, and we have d over dx. Derivative of two functions multiplied is the derivative of f of gx times g of x is just f prime of x times g of x plus f of x times g prime of x. And if we simplify this down in terms of the functions that we're actually dealing with, we get that f prime of x is 1, right? Times g of x, which is y of x, plus f of x times g prime of x, so plus x times y prime of x. In other words, what we've done is we've been able to simplify this down all in terms of y of x being a function, and we've just treated y as its own function and taken the product rule. Now, going further from here, remember, we can just go back and write y of x as y, so you get y plus x times the derivative of y. And the derivative of y will represent as dy dx. And that's pretty much it. And traditionally, you'll see the y prime of x, you'll see it written in a couple of ways. You can see it written as d over dx of y of x, right? The derivative of a function y in terms of x, you're taking the derivative with respect to x, but you'll also see it sometimes written as just y prime. And all of these kind of mean the same thing, and you'll also see it written sometimes as just dy dx. In other words, the derivative of y with respect to x. And so in this case, we can write y plus x times dy dx as just y plus x y prime. Now, let's try another example with this just so we can kind of understand what's actually been happening. Let's take the example xy squared. Now, this one's a little bit more complicated, but let's do what we did last time. Let's treat y squared as its own function. We treat y of x, y is equal to, say, another function, right? Let's treat it as its own function g of x, right? Well, now notice that we're doing y squared. So it's kind of what we were talking about before with the chain rule, right? We're basically squaring this function g of x, and we're multiplying it times x. But to take the derivative, remember what we said about product rule. You take the derivative of the first function, so in this case, derivative of x is 1, and you multiply it times the second function, plus the first function, times the derivative of the second function. What is the derivative of g of x squared? Well, the derivative of g of x squared is the same as saying, okay, let's introduce a new function. H of x is equal to x squared. We want h of g of x. We want the derivative of that. We can write that as h prime of g of x times g prime of x. In this case, that looks like the derivative of x squared, which is 2x, so 2g of x times g prime of x. In other words, the derivative of y squared is going to be 2 times g of x, which we said was y, times g prime of x, which is y prime. Another way you'll see this explained a lot of the time is whenever you take the derivative of any function of y, you just take it as if it's a regular derivative in like x, but then at the end you add on a y prime. Essentially, that's what we've been doing. If you notice the last example, when we did derivative of x times y, you do the product rule. You'd write it as 1 times y plus x times the derivative of y. Well, we'll say the derivative of y, we use our product rule, right? It's y to the power of 1. You bring the 1 down. Y to the 1 minus 1 is 1. X times 1. But then you have to add on a y prime at the end. So you end up with y plus xy prime. And we can try that with the other example, right? When you have xy squared, all we're doing is we're treating y and we take it as derivative of x is 1. So you do 1 times y squared. And then from there, we add it to x times derivative of y squared would be 2y. And then you have to make sure to add on your y prime at the end, and we're done. Okay, but let's try to do a more difficult example with this. Let's say that the question is something like x over y. Well, what do we do now? This one's much more complicated because it uses our quotient rule. We do low d high minus high d low all over low squared. So in this case, low is y times the derivative of the higher function, which is 1, minus high d low. What's the derivative of y? We said y, you write it, derivative of y is 1 equals 1 times y prime. So you get xy prime all over low squared. Low squared is just going to be y squared. And we're done. Y minus xy prime all over y squared. And a lot of problems, what they'll say is they'll give you some function. They'll say, what is the derivative of, what is the value of y prime? And so how do we go about doing that? Well, let's take the example of x times y cubed. If we take the example of x times y cubed, and we want to find the derivative. Actually, let's do x squared times y cubed. We first do the product rule. You get 2x y cubed, right? Derivative of x squared is 2x. You do 2x times y cubed. And then you add it to x squared times the derivative of y cubed, which is 3y squared times y prime. Remember, you have to add on that y prime at the end. But now how do we go about solving this? Let's say that the function is this, equals 1. Or let's say it equals 0, right? Actually, let's just say this is some function, right? And they want us to solve for the value of y prime. Well, if our function is, say, x squared y cubed minus 4 equals 0, remember, that means that this derivative would equal 0. You take the derivative of both sides, you get 0 on the right side, and you have what we solve for on the left side. Now we need to solve for y prime, right? So to isolate y prime, we bring over the 2xy cubed to one side and keep the y prime on the other side. So you get x squared, 3y squared times y prime is equal to negative 2x y cubed. Now, if we simplify this down, we get y cubed is equal to negative 2x y cubed all over x squared times 3y squared. And we can go a step further and we can simplify this, and you get negative 2y over x. So this is just a quick summary of what we're doing with this logarithmic differentiation. But how does this actually help us for the example we were doing before? Well, in the example where we had ln of y is equal to the derivative of ln of y is, let's just copy this whole thing and move it down. And let's see how we can actually finish solving this problem. Now we had y equals x squared times 1 minus x to the fifth all times 2x cubed. We take the ln of it, and you get ln of x squared times 1 minus x to the fifth times 2x all cubed, and we simplified it down. Now, once we get to this step, we can basically now say, okay, this is ln of y. Now let's take the derivative of both sides. Well, now using our knowledge of implicit differentiation, we can solve for the derivative of ln of y. Okay. The derivative of ln of y. Remember what we said about ln of a function? The derivative is just 1 over y. But remember, you have to multiply times y prime because of the fact that it's y, not x. Now, the right side, we said the derivative was 2 over x minus 5 over 1 minus x plus 3 over x when we were solving it before. Now, that means that y prime is equal to y. We can multiply the y to the right side. You get y times 2 over x 5 over x minus 5 over 1 minus x. And if we were to plug in our value of the function x squared, this whole function y, and multiply times 5 over x minus 5 over 1 minus x, we'd get our value of y prime. Okay, so now that we've gone over how to do this logarithmic differentiation and how to do implicit differentiation, now we can take a step further, and now we can talk about derivatives, but of higher numbers. In other words, higher order derivatives. And so higher order derivatives are going to be when you take the derivative multiple times. So say that we have our function sine of x, right? We start off with the function sine of x, and we take the derivative once, right? You get f of x equals sine of x. The derivative of sine of x is cosine of x. But imagine now we go a step further and we want to take the derivative again. The way we denote that is by putting 2 degree signs. We put 2 primes, and that represents the second derivative. And if you put 3 primes, then you get the third derivative, 4 primes, the fourth derivative, so on and so forth. Well, the derivative of cosine of x is negative sine of x. In other words, the second derivative of sine of x is negative sine of x. And the way you can also denote this is writing it as f2 of x, where you put 2 in the parentheses. A common way you'll see this written is f of n, written like this, is going to be the nth derivative of x. It's the nth derivative of the function of f of x at x. So now let's see how we can use this in other ways. Say that you have x to the fifth plus 4x cubed plus 2x, and they want us to find what is the third derivative of x. Well, the way we would solve this is by saying, okay, first, what is f prime of x? That's equal to 5x to the fourth plus 12x squared plus 2. And this was just done using our power rule. But then what is f second derivative of x? That's 20x cubed plus 24x. And if we want the third derivative, you bring down to 3 and you get 60x squared plus 24. And we're done. So for higher order derivatives, it's just going to require a little more work, but the basic idea is still the same. You're just taking the derivative much more times. And that's basically all there is to it. There's one thing we didn't talk about, and that was fractional powers. So the power rule also applies for fractional and negative powers. And what do I mean by that? Say you want the derivative of x to the 1/2. How would we go about doing this? Well, the derivative of x to the 1/2, you can still use the power rule. You bring down the 1/2 x, but this time you do 1/2 minus 1, and you get 1/2 x to the negative 1/2. And so that's what you have to be clear about when you're dealing with these exponents that are not integers. You have to make sure when you subtract 1, you still keep it as a fraction. And so in this case, you can simplify this down as 1 over 2 square root of x. Finally, you can also do negative powers, but you have to be very, very careful with these. Imagine you have x to the negative 2. The derivative of this, if we want d over dx of x to the negative 2, what we can do is we can say, okay, we bring down the negative 2. So we write x to the negative 2. We bring down the negative 2, and you get negative 2x to the negative 2 minus 1, which is negative 2 x to the negative 3. And so notice that the exponent went from 2 to 3, but the reason it does that is because you're going down by 1, but because it's negative numbers, when you go down by 1, the number goes from 2 to 3. Finally, we can finish off by doing another example of this, but when it involves something like, we can do higher order derivatives, but when it has something like y double prime. So what is y double prime? It's the second derivative of a function. So imagine the question says, what is the second derivative? So what is y double prime of x? What is y double prime of x, where y of x is equal to, say, 1 minus x all over x squared. So this is going to be a classic example of our quotient rule. So what we can do is we can say, okay, low d high minus high d low all over low squared, which is x squared squared, so x to the fourth. So what we've done here is the lower function times the derivative of the upper function minus the upper function times the derivative of the lower function all over low squared. And you'd get negative x squared minus 2x minus 2x squared. And we can go further and we can simplify this down as negative x squared plus 2 minus 2x plus 2x squared all over x to the fourth, which is x squared minus 2x all over x to the fourth. We can cancel out an x, so you get x minus 2 all over x cubed. But stop, the question did not ask for y prime of x, it asked for the second derivative, the y double prime of x. So we have to take the derivative again, this time with x minus 2 over x cubed. So low d high minus high d low all over low squared, so x to the sixth. This ends up being, we can cancel out an x squared, so you get x minus 3x plus 6 all over x to the sixth, which is negative 2x plus 6 all over x to the sixth. And so when you take higher and higher order derivatives, all it requires is a lot more work, and you just have to make sure you keep taking the derivative until you get to whatever you want. And so sometimes you'll see problems say, what is the second derivative of x? But they give us a value of x. Say they say at x equals 2. Now we simply have to plug in our value of x is 2. So we plug in negative 2 times 2 plus 6 all over 2 to the sixth, which is 2 over 64, or 1 over 32. Now, what I'm going to do is I'm going to give a few minutes to work on a practice problem. What is the second derivative of cosine of sine? What is the second derivative of cosine of 5x? What is, if this is the function f of x, what is f double prime of x at x equals pi over 2? Or we can say at x equals 0, just to make it a little easier. Okay, so going over this problem, we say, okay, the function is cosine of 5x. So the derivative, the first derivative, so f prime of x, is equal to negative 5 sine of 5x. And so why is that? So we use our chain rule, right? Doing the chain rule, we get that this is, we take out we do first derivative of cosine x is negative sine of x. So it's negative sine of 5x times the derivative of the inside, which is 5. So you get negative 5 sine of 5x. Now, if we take the derivative again, you get f double prime of x is equal to negative 25 cosine 5x using the same strategy we talked about before. And plugging in our value of 0, you get the final answer f double prime of 0 is equal to negative 25. Good job. Okay, the final trick I want to go over is a really fast way to do implicit differentiation. So implicit differentiation, if you remember, was when we were solving for our y prime, when the equation we were given included y, like products of x and y. So for example, the example we did with like x, y squared. A very, very fast way to do something like this, like imagine the problem is xy squared plus y cubed plus x squared equals 1. How do we go about taking the derivative of this and finding y prime? Well, if we want to know what y prime is, there's actually a very fast way. It's when you take the derivative with respect to x over the derivative with respect to y. So we take the derivative, I'll just write it like this, over d over dy. Although this isn't the official notation, we can just think about it like this. If you take and then take the negative, this is going to be the value of y prime. In other words, you take the derivative of the function with respect to x and then divided by the derivative of the function with respect to y, and then take the negative of it all. This is going to look something like this. Taking this whole function, taking the derivative with respect to x, we'll get y squared plus 2x. And so there's a lot going on here. Let's take each term one at a time and see how I got this. First, let's look at xy squared. When you're doing this strategy, you don't care about y at all. You treat y as a constant, essentially. So y is just the coefficient of x. So we'll write it as y squared times x. And the derivative of x we know is just 1. So when you take the derivative, let's say that y squared, just replace y squared. Y squared is just like, say, some value a. The derivative of ax we know is just a. Similar to that, the derivative of y squared times x when we're using this strategy is just y squared, which is where we get this first y squared. Now, the y cubed is just the equivalent of a constant, and the derivative of a constant is just 0. Finally, x squared we know is just 2x. In the denominator, we have to take derivative with respect to y. So in other words, we treat x as a constant and take the derivative based on y. So that means that when we look at xy squared, the derivative of xy squared with respect to y, because x is a constant, you say, okay, y squared, the derivative of that is 2y, and then you tack on the x because it's just a constant that you're multiplying by. It's similar to what I talked about before when you had x times y squared, and you just took the derivative, got 1, and then multiply times y squared. So the denominator is going to be 2xy. And what do we add it to? Well, notice that the x squared does not matter because it's just a constant. We're treating x as a constant. And then y cubed, the derivative is 3y squared. Finally, we take the negative. So we get our final answer is the negative of y squared plus 2x all over 2xy plus 3y squared. And why is this very useful? It means that if they say 2 points, say they say that x is equal to, let's say they say y is equal to 1, and then they say x is 0. So they say at the point, what is y prime at the point 1, 0, or 0, 1, I should say. Well, what makes it really convenient is you can just plug in our values for 0 and 1. We say x is 0, y is 1. So you get negative of y squared, so 1 plus 0, all over 0 plus 3, which is negative 1/3. And this is by far the fastest way to find the derivative of anything that requires implicit differentiation. It's much faster than writing it as like y prime and doing it step by step. and then isolating for y prime, it's faster just to do negative partial derivative of x over partial derivative of y. And the reason it's called a partial derivative is because you're treating the other variable as just a constant essentially and taking the derivative and then dividing it by the other variable being treated as a constant. And that's pretty much all there is to it. Okay, Ritvik, I see that you're here, so I think you can just like start teaching. We basically finished covering basically all we needed to.
Okay, cool.
I'll stop sharing screen and then you should be able to.
All right. So this is a pretty interesting Putnam problem I found. I was doing earlier last week, and I thought it was pretty relevant to some of my FAMAT problems, but I thought I'd introduce it and talk about the logic behind it. Okay, so this says a game involving to the right on the real number line. If A and B are real numbers and B is greater than A, the cost of jumping from A to B is, some arbitrary expression. For what real numbers C can one travel from 0 to 1 in a finite number of jumps with cost exactly C? So the first thing we need to do is that this is a pretty wacky expression for the cost. So this is B cubed minus AB squared. But actually, let's first start about the motivations. Again, this is a Putnam problem, meaning it's proof-based, and we need to rigorously define the conditions for what we're doing. So what exactly does this tell us? Well, we need to find three conditions. One, we need to show the minimum bound for this. We need to show the minimum bound for C. Two, we need to show the maximum bound for C. And three, the hardest part in general when you're trying to find intervals of convergence or intervals for anything, the hardest part is ensuring that every other value in the series actually ends up working. Right, so this is probably the hardest part of the problem. So what we end up doing is we start factoring this. So this is B squared times B minus A. Now off the bat, this doesn't tell us anything immediately. Well, what you notice here is that B minus A is actually the length of the interval that we end up jumping or making the jump from or move from. And B squared is the end of the function. So it actually implicates a lot more with the cost function and we haven't even looked at the graph yet. So what this tells us is that this is actually the area of a rectangle that has length B minus A and height B squared. Correct? But it's very different because what happens if we make B minus A super small? What if we keep making finite infinite moves, which means that we only go like a little bit and a little bit and a little bit, but we still end up reaching 1. This base is going to get smaller and smaller, but the height still maintains the same because B is not changing. B is just relatively close to A, but again, relatively close. So what this ends up being actually is a pretty good estimation for a Riemann sum under the curve x squared. Now, how do I say this? If I draw the graph x squared, my rectangle that I make right here, actually I should draw it like this. Let me draw it a bit bigger. Right? I'm constructing some rectangle that intersects at the vertice here. This rectangle now has height B squared because this is at interval B and A. So what that means is that I'm now constructing a bunch of these rectangles like this in an effort to estimate the area under the curve. That means that my cost of making infinite moves to get to 1 is actually pretty resemblant of the integral from 0 to 1 of x squared dx, because that's all this rectangle is I'm going to end up estimating the area under the curve, because I have, again, going back to the definition of an actual Riemann integral, it's in effect, we're just adding up a bunch of areas of rectangles. We're adding up the base, which we typically denote as del x, and then the height, f of x sub I, depending on which subpoint that we choose to select. In this case, it's the same exact thing, except we're doing a right Riemann sum, because we're selecting the rightmost endpoint of this thing. So this is obviously, this integral is not hard to evaluate. This is just x cubed over 3 evaluated from 0 to 1, which is 1/3. But now this is where it gets interesting. This is the theoretical minimum. This is if we reach infinite rectangles and we keep constructing rectangles, constructing rectangles underneath this curve. This is really close to the Riemann sum. But the issue is that it overestimates. And why is that? Well, we learned in Calculus AB, if you've taken that, but if not, I'll do a quick recap. Of Riemann sum, or any estimation for that matter, numerical estimation, overestimates the function if the concavity is positive. In this instance, x squared has a second derivative of 2, which is always positive, clearly. So that means it's whenever we do a right-handed Riemann sum, we're going to be overestimating the area of the function. And you can confirm that graphically, or visually rather, is because every time we construct the rectangles, obviously this is a pretty inaccurate representation, but there is so much area that we're saying here is above the graph, really, and has really no relevance to what's under the graph, but our estimation still accounts for it. So we've now determined that 1/3 is the absolute minimum. That it cannot go any lower than that, because that would imply there are infinite moves. And we're told that it's a finite amount of jumps. So 1/3 can never be reached. It can always be greater than 1/3. It would have to be a pretty close to infinite amount of moves, but 1/3 can never be reached. So for those of you more interested, this is what we call an upper Darboux sum, D-A-R-B-O-U-X, a Darboux sum, which is where we construct these rectangles stacking on top of each other. And so the Darboux integral for this would actually exactly be 1/3. But because we're doing a regular Riemann integral, this ends up only being a little bit greater than 1/3, because again, it's an overestimation of the actual area. But it's neat how we were able to derive from just the cost function itself that we're already able to prove the minimum bound. So does this make sense to everyone so far? So now we've determined that the minimum is non-inclusive 1/3. It's all good for everyone? Well, okay. It'll be good for recording, I suppose. I thought there'd be more people, honestly. Well, at least you guys are, I don't know if you guys are winning. Okay. All right, so the maximum here, well, this is pretty obvious in and of itself, is that if we only do one finite jump from 0 to 1, we can end up ensuring that, well, the cost function is quite literally just going to be 1 cubed minus 0 times 1, which is just 1. So that means that the maximum is always going to be 1. I can only do, since I'm ensured that I have to do at least one jump, I can jump directly from 0 to 1. I hit my maximum. I'm not going to go into the rigor of it. That's quite literally all you need to write on the Putnam, is that the interval now is that we'd be able to say this is C is in the interval from 1/3 to 1 inclusive. So we said the max is equal to 1. All right, so people are joining, or Tom may join. So as a recap, actually, I'm not going to recap. It took a while. You can just watch the recording. So now we've proven the minimum and the maximum, correct? Those are established. We were able to prove it rigorously. With the minimum, we showed that we're always going to be overestimating the area, which means that we can never actually reach the Riemann integral under that curve, which is 1/3. And the maximum here is just going to be 1 because we'd only do one finite jump. Now the question remains, how do we end up proving that everything else in between, that it can obtain every other C value in between? Lower and upper bounds, something so. Technically speaking, yes, but for the purposes of just dealing with the cost function itself, like if we were taking only just A to B and we kept partitioning it, I guess I should say the limit of whatever Darboux approximation that we're going to take is going to get to 1/3, but you're correct that it wouldn't actually end up equaling 1/3 precisely. But yeah. For the purposes of the Putnam, we wouldn't really need to go any further. We've already shown that it's an overestimate, A, so that means it has to be greater than 1/3, and we've also shown that the exact area under the curve is just is 1/3. So now we need to show that everything else is in between, and this is probably the trickiest part of the problem, in that we have no actual way of ensuring that any subsequence we select is going to converge to some value within this interval. So what I ended up doing is, for purpose of not boring everyone to death, I ended up just saying, okay, so I made some sequence of jumps, x1, x2, all the way to x7. And I said that this subsequence right here had cost, I definitely already predetermined cost C sub n. Now imagine that I entered a new jump here. I said, okay, let me split this up further. Instead of 0 to x1, I just shove in a random value like x question mark. How does that change the cost if I insert some arbitrary new jump into the mixture? So 0, now our new subsequence is 0, x question mark, x1, x2, so on and so forth. And so our new cost of this function, or a new cost of these set of jumps, is going to be C sub question mark. So then what I then tried to show was C sub question mark, what it now equaled. Well, it's going to equal the initial cost, which is C sub n, but there are two new jumps involved, from 0 to x question mark and x question mark to x1. So the cost from 0 to x question mark, remember that the cost function was b cubed minus ab squared, where the interval is from a to b for jumping. Then we're left with, this is x question mark cubed minus, again, a is effectively 0. So 0 times x question mark squared. And then the second additional cost is jumping from x question mark to x1. So this would be x1 cubed minus x question mark x1 squared. So now we have a definite evaluation for this. This is simply just that. We can then factor x question mark here is going to be, factoring that out, it's going to be x question mark squared minus x1 squared plus x1 cubed. Now, what was the overall purpose of this besides just writing stuff? The goal here was that I inserted some random value here, 0, x question mark, and then x1. But the goal here is that I want x question mark to disappear. I already set, I want to approach this. This is my desired limit. So what I end up doing is that as I, make x question mark approach either like very, very close to 0, so that the cost of that jump is so small, I'm actually able to show that this varies across all values from as I let x question mark go between these two values. I'm able to show that this, in fact, actually does give us new values of c from our lower bound of 1/3 to our upper bound of 1. Oh, this is inclusive, actually. So I thought it was pretty cool that we were able to do this. We were able to show that by inserting a new finite jump in the sequence of whatever original sequence we had, we were able to show that it converges eventually to c sub n, which is the original cost of all the original jumps made. But by inserting an element, I'm able to add that additional cost and show that it is necessarily going to be greater than 1/3. So now I've shown pretty rigorously why I'm able to insert that extra jump and why it does greater the cost of overall such that it's between 1/3 and 1. But for a more rigorous proof, I can say, all right, let's select some, let's say that the x coordinates are all proportional, right? They're all proportional to the value that I'm selecting them at. So they're all equidistant to each other. And again, this goes back to the concept of the Riemann rectangles, but instead I'm not approaching infinity. I'm just going to say it's finite as of now, right now. And I have these equidistant rectangles right here. So what I end up doing is I can just directly evaluate the sum. So we said that the total cost C, there's no difference of C. This is the sum of C sub I from I equals, 1 to infinity. Now I can actually just let it approach infinity, or just always, I could write it as the limit as n approaches infinity, but in effect, it's the same thing. All right, so we're told that the cost function here we said was x sub I plus 1 cubed minus x sub I times x sub I plus 1 squared. So putting in our definition for x sub I here, this is I cubed over m cubed. This is going to, and then m is, I guess, in essence, the division of the how many intervals we want. Again, this is the typical Riemann definition of what we're approaching. X sub I is simply just I over m. And then this is I plus 1 squared over m squared. So this equals, well, we have to just expand this a little bit. This is I equals 1 to infinity. This is I cubed minus, and the numerator is I cubed yes, that is also I plus 1. Oopsies. So this becomes I cubed plus 3i squared plus 3i plus 1 minus I cubed minus 2i squared minus I, all over m cubed. I cubes cancel out. I should actually write this as the limit as m approaches infinity. And then we're going to bound it at m. Make our life a bit easier. I cubes cancel. We're left with I squared. Yeah, I squared minus 2i plus 1 all over m cubed. The rest is irrelevant to us, the 2i plus 1, because that's going to be asymptotic to 0 when we approach m equals m cubed, especially. So all we care about is the I squared, because we know that's going to evaluate to something. So we can factor out 1 over m cubed. This sum is the sum of squares from 1 to m, which is simply m times m plus 1 times 2m plus 1 all over 6. Clearly, there's an m cubed, going to be a 2m cubed term up top, plus whatever O sub n squared. That's all going to be convergent to 0 as m approaches infinity. All over the initial 6m cubed. This disappears. We're left with 1/3. And of course, this is obviously what we confirmed in an earlier result, that when we actually do the regular integration, we're going to get 1/3 as the area. But now we've ensured that the limit of the cost function, or the sum of the costs rather, is going to approach 1/3. However, approach in the sense that this is the global minimum of the cost function that we were told. So therefore, at this point, we've now rigorously shown that the cost function, or at least the cost itself for some value of selected C, is going to be between 1/3 and 1, non-exclusive, or exclusive and non-exclusive respectively. So yeah, I think that was a pretty cool problem, something that's not entirely out of the reach compared to the other Putnam problems. But I think it's a nice concept to talk about, like cost functions and how we can end up structuring them. I think I made a mistake with the Darboux sums. I only looked into it after I solved the problem, so it's possible I'm just unfamiliar with the concept. So I just vaguely remember reading about it. So I think it's cool though, this cost function type thing. And so if anyone's watching this recording or something, this is a pretty cool concept and may show up on future tests. ? Wink.
So thank you if you like sat through all of this or like watched all of this. Thank you, Rithvik, for coming and showing us a cool problem. And yeah, if you have any questions, you can email the FAMAT Delegates email or anything like that. And yeah, thanks for watching.